do our first example of continuous Fourier transforms. It's hip to be square. So plotting vertical lines in mathematics is not easy, so I'm just going to draw this in. So we have a square wave here. So it goes from 0 to pi, 0 to 2 pi. We have time in seconds right here. So to do continuous Fourier transforms, we need a couple of things. The first thing is that we need to know the algebraic form y of t. So can we figure out, so first off, CFT versus DFT, one quick tip. If you see lines, typically, obviously, you might use CFT. If you see points, discrete data sets, or table points, you see dots, this point plot, that you can't, find the algebraic form, then you want to use discrete Fourier transforms. So just kind of a tip to kind of identify. So lines, we're looking like for CFT. Can we describe this equation algebraically? Well, you might be concerned about this discontinuity here, but we could describe it piecewise. So from a time value of 0 to pi, we will find that y sub 1, I'm going to call it, a function, is going to be equal to just 10. And from times from pi to 2 pi, my y2 of t is going to be equal to 20. So that's it. And then the material repeats. So what else can we extract from this graph? Well, my period, the shortest time over which that will repeat, is just going to be 1 over my my fundamental frequency, delta f, is going to be 1 over t. But my period here, so I go from flat, up, down, flat again. So that period is 2 pi seconds. So I've got my period, I've got my delta f. Well, and I know that I'm going to plot my frequency spectrum, so my c sub n, as a function of delta f, and I know that each of my harmonic coefficients, c sub 1, corresponds to a 1 times delta f. My c sub 2 is going to be equal to, or not equal to, but it corresponds to 2 delta f. So again, this is my value, c sub 1, and this is delta f. This is 2 delta f, and this could be like c sub 2, whatever that y-axis value is. That's what I'm going to plot. So that's all we're going to do. So nothing's too, again, don't be too intimidated by Fourier transforms. We're going to keep it nice, and straightforward and engineering focused in this class. So here's my functions. Here's my a sub n and b sub n values, and we'll just go ahead and do the integration and calculate it out. So this one's straightforward enough. Again, we've defined our period, and now we could just kind of plug in for all these different values. So we know y sub 1, we know y sub 2, we know that t equals 2 pi seconds, and now we're just going to do the integration. So you can integrate this by hand. We're going to show you in the next video just how to plug it and write a code in Mathematica. Remember, if you plug in for any value of n, that harmonic coefficient is going to be equal to 0. There's a unique, whenever you're dealing with the 0th order harmonic, so a sub 0, b sub 0, we just want to directly plug in. So before we kind of do this analysis, it's just going to be a sub 0 to be equal to 2 over t, 0 to t of my y of t. What is cosine of 2 pi n t over t when n equals 0? Cosine of 0 is just 1. So it's just going to be y of t dt. That's it. B sub 0, what's sine of 0? It's going to be equal to 0. So that's how you deal with those 0th order harmonics. But for every a sub n that n is not equal to 0, a sub n is going to be 0. Yep. So we can go ahead and do that, and we could calculate those harmonic coefficients, the magnitude of those. So this is on our frequency spectrum graph. That's our y-axis value. We're going to plot cyclic frequency on the x-axis. So again, our delta f. And again, you could kind of redefine. So our period was this, or 2 pi. The cyclic frequency is 1 over 2 pi. X-axis will be n delta f. You could actually rewrite those expressions and plug in. So instead of as a function of t, you could write it as a function of f to help you visualize it a little bit better. But again, it's easier. It's kind of harder to measure f, our fundamental frequency, or our lowest frequency. So you could also rewrite this in terms of delta f. This is a little bit harder to measure or kind of conceptualize. So on a graph, you could easily kind of measure t right off and then calculate delta f. But again, if this will help you kind of better visualize why we're plotting n times that delta f, this will be a little bit helpful. So, but once we do that, and we're going to get a graph like this. So this is our frequency spectrum. C sub n, the amplitude, as a function of frequency, cyclic frequency. So I can see directly from this signal, this is my lowest frequency, or my highest frequency, excuse me. This is my f max for these harmonics. And this is going to be a function. I actually know that f max is going to be equal to n delta f, where n is our, so typically when you're doing a continuous Fourier transform, you plot from, like, let's say, give me the first, like, 10 harmonics. So in this case, n would be 10, and from this value, you could actually back calculate what is your delta f. Or you could just look at this frequency here, the first non-zero frequency, that is going to be a delta f value. And actually, these spacings are going to be in interval spacings of delta f, because I know that this is also 2 delta f, because it's integer values. This is 3 delta f, this is 4 delta f, etc., etc., etc. So this is my lowest frequency, this is my maximum frequency here, this dot, and we also know that there's a dominant frequency. The dominant frequency has the highest amplitude, the highest y value, and that, in this case, is going to be also, our fundamental frequency is also our dominant frequency. So that's it. We're our Fourier masters. So next time we are going to get into how we can then utilize this. Except this is essentially what we've kind of talked about previously here: maximum frequency or signal, dominant frequency. We're going to actually solve this kind of mathematically, and we'll get into kind of the one of the key aspects always is what is the fundamental reason or the physical insight we could give or gain into this Fourier spectrum analysis. The dominant frequency is an important parameter to kind of see. In lab, we're going to figure out the natural or resonant frequency of an aluminum beam using this type of analysis. So we're going to take a beam, we're going to deflect it, it is going to vibrate. We're going to take that acceleration signal, convert it into a frequency spectrum, and you're going to see nothing and then a spike. We want to make sure that this dominant frequency here does not match like the natural vibrations it might experience in an application, right? So if I have a beam and it's a structural application, so like this aluminum beam, it's under some load, but there's some frequencies from, like, say cars driving by. Ooh, I'm becoming an artist. If there's some vibration here that matches this resonant frequency, that beam is going to oscillate, and those cars are going to be in big trouble. So this is the key power of Fourier analysis. We can look at this graph and we can make engineering decisions and really avoid catastrophic disasters and loss of life. So the different vocal frequencies, or it's boundless. So that is what we're going to actually do the code, write it out, make it more general, and solve it explicitly in Mathematica next time. And then in the next video, we're going to get into our representing a Fourier series. So I'll see you all next time. Thanks. Have a good one. Bye.